So number 36, after our sun exhausts its nuclear fuel, its ultimate state is to collapse to a white dwarf. A white dwarf has approximately the same mass as the sun, but its radius would be equal to the radius of the Earth. It's still white because it would just residue heat, but its density would be crazy large. And that's actually what we're calculating in A. Real quick for A, if you forgot what density is, it's mass over volume. Plugging in the mass of our sun, and if you remember, the volume of a sphere is 4/3 pi r cubed. Plugging in the radius of the Earth, because it now will be that size, and doing the math, you get its density. It's about 1 trillion kilograms per cubic meter. Or, to put in perspective, a teaspoon of white dwarf material would weigh as much as the Queen Mary. Part B, find the surface freefall acceleration if you're standing on a white dwarf. So remember, G, acceleration of gravity, is just equal to G, the universal gravitational constant, times the mass of the object over its radius squared. In this case, plugging in our numbers, it's going to have the mass of the sun, but the radius of the Earth. And if you plug those numbers in, you get this absurdly large acceleration. After falling 1 second near the surface of a white dwarf, you would gain about 3 million meters per second. Please realize G would not be constant, that constant there, but still unreasonably large. C, the gravitational potential energy associated with a 1 kilogram object at the surface of the white dwarf. So here we've got to use GPE on a much larger scale. So negative G times M1 times M2 over R. And plugging in our numbers, mass of the sun, 1 kilogram object at the surface of this planet, and you'll discover its gravitational potential energy negative 2 times 10 to the 13 joules. In other words, you'd have to add 2 times 10 to the negative 13 joules to remove the 1 kilogram object from the surface of the white dwarf. A crazy amount of energy. I hope this helps.